Well, you only get one landing if you make them out of feathers. Dr. Lewis, thanks for coming. Appreciate you being here. You mentioned that artificial photosynthesis could benefit from modeling and simulation using high-performance computation systems. Is that something that the research community has begun to discuss with DOE?
I believe so, but not in such an organized fashion as to establish a separate program for high-performance computing applied only to this problem. But there are specific examples. I'll give you three briefly. We discovered a nickel-gallium alloy just recently in our laboratory that selectively takes energy-efficiently carbon dioxide and makes interesting carbon-coupled liquid and gaseous products. That was predicted by theory before we did it experimentally. Now, it turns out the theory got the energy efficiency right, but it got the carbon products wrong. They predicted methanol. Well, that's because the theory was done on an ideal surface with perfect atoms, and the real sample we made had all sorts of nooks and crannies and edges that then we have to iterate back to tell the theorists, well, now you've got to predict what the real world samples are, but they got it close enough to tell us where to look. The second point is that theory has predicted out of 19,000 metal oxides, 200 that might be stable light absorbers under our conditions. We don't yet know how many of them can be made outside of the computer and exist, but now we're looking there to try to have a guide from high-performance computation into where the experimental work should be done, and then refine it. So that would be the optimal way, in my view, to not have the world just abstracted in computer. We have to build it, we have to make it, and then we have to find out where the theory is right and wrong, and then iterate back and forth until we get to where we need to be.
Just like any test or experiment, you've got to have a theory, and then you've got to actually see the ability to see it practically work. I want to go to Dr. Hallinan about the batteries. And Mr. VC was talking about Texas. Well, in California, we have quite a bit of photovoltaics and solar and wind and all kinds of renewable energy products there in the Mojave Desert. Our biggest problem is battery storage. Our biggest problem is the wind is not always blowing and the sun is not always shining. And so if we want to move to our new RPS, which is our new renewable portfolio standard of 50 and then 60 and 70%, we might get to that line where we can't go any higher. We've got to burn something because, like I said, the wind's not blowing and the sun's not shining. So we've got to burn something to keep the lights on. At what point, or how close do you think we are, and this might be a question for everyone, at what point do you think we are that we can store something that comes from a 1,100-acre field out in the Mojave Desert that is producing a huge amount of energy, but we are burning that energy, or we are using that energy very quickly, instantaneously?
So that's a challenging problem, and I think there are a number of constraints that we face. So one is we don't want to be spending large amounts of money to make these batteries just to store this energy for a short period of time, right? So we have this cost constraint, but then we also want these batteries to last a long time. We don't want to have to be replacing them regularly. We also need them to charge and discharge at a rate commensurate with either the production or the consumption of the energy. And so So when you look at batteries, there's a very wide array of different types of, we call them battery chemistries. Lithium-ion are very good for portable electronic devices, and they're now being used in electric vehicles. Nickel metal hydride are used in hybrid vehicles. So there are many different chemistries. I think what Dr. Scherson mentioned earlier about these redox flow batteries, they seem to be the most promising for what I would call stationary storage. So where if we don't need to move the battery around, we really don't care how much it weighs or how large it is to some limit. We care mainly about cost and it satisfying the other needs of storage. And so, I think for grid storage, really these flow batteries, and the reason they're so interesting is once you've designed the electrodes, then if you need to scale them up, you just make a bigger tank of your liquid that you're going to flow to the battery. Now, I would say, they're still at the research stage, but they seem the most promising from what I've seen.
So I'm going to, the chair will allow me just to ask one more question. I'm going to put this back to Dr. Lewis because I think he understands this. What we go through in California, what we go through in Texas, what we go through in some of the states is that is the issue, is not, well, the land is an issue, but we have a lot of land that we can put these 1,000-acre fields out there, and it does become an issue more politically than for the science community. But that will become a problem. If we cannot store this energy, if we cannot use this energy at a later time, then we might be on the wrong technology. And I say that just personally. We might want to look at something else, because if we cannot store this, we are going to be using so much of our land that I think that it might be a problem. And the second question, I'll give this to you too, is we've got car companies coming out, and they're doing cars that can go about 225 miles on a charge, and exactly what Dr. Hallinan said, we would change out the batteries at changing stations instead of filling up your gas tank with gasoline, and that could be a problem because now we're producing all of these batteries. We're going to have a huge amount of batteries if we've got 50 million cars on the road and we have to have 100 million batteries out there at just changing stations. I think that that's a problem with this technology, but it could just be me.
I'll at least try to address the first question. Storage is, in my view, I agree with you, the #1 problem to think about actually at scale deploying intermittent renewable sources. We have technologies that are reasonable at solar and wind, but if we can't store, we can't have power after 4. It's pretty simple. We should do this broadly. You should think about ramping up and down nuclear power plants fast in certain designs, about natural gas-fired power plants, about demand management, about making fuel directly from the sun, about batteries. There are probably lots of ways to think about this. Storage of electricity has been realized as a gap since Thomas Edison noticed it in 1931. And we have to solve this problem. This is where I think a broad program, not just in batteries, but in all sorts of technology options that can help us meet load in the face of a dynamically changing energy market, are critically important. With respect to the battery recycling, that solves one problem and introduces another. It solves a problem in that there won't be a rapid recharge of a battery by electricity for a very long time because all batteries have what's called an internal resistance that prevents them from shorting. If you try to charge them up, you dissipate so much heat through that resistor that you would boil all the liquid in your car if you tried to do that in 5 minutes. So instead, you swap a battery out with a previously charged battery, and the problem, of course, is now you have at least twice as many batteries on your hand you have to move around. This, again, points to what would be a dream solution of if instead you could make liquid fuel and store the energy that way, then you could convert that electricity into stored fuel, and we know how to handle that. So there are lots of things we should be thinking about. These are incredibly important problems, and we need to do a lot more research in order to try to make them into reality.
Thank you very much. Thank you, Mr. Chair, for the indulgence.